The forests of our Earth have various effects on climate and life. Starting with the central role for carbon storage, air pollution control, storage of drinking water, to the significance as a habitat, recreational and tourism attraction. They offer a diverse spectrum of services. The predicted climate change puts trees and forests in front of a great challenge. Each tree species has specific requirements on its habitat. It only grows optimally if the required living conditions are present. Not every tree species is suitable for every site. We're talking about the ecological amplitude each tree species possesses, which is defined fairly clearly. With so-called climate envelopes, the optimal living conditions can be visualized. For this purpose, average annual temperatures are determined for different locations and are shown on one axis of the diagram. The value of the annual precipitation sum, for example, is shown on the second axis. The distribution of the measuring points results in a simple climate envelope that demonstrates under which circumstances that particular tree species is able to grow. A variety of additional factors such as type of soil, tree density and age, but also available soil water, can be put on additional axes and define the habitat more precisely. If, for example, the soil water availability decreases, the climate envelope will show that there are locations where the tree species in question could have problems. One of the most important factors here is the water supply of the trees. When we look at the water supply of trees, there are four important components. There is the natural water absorption through the root, and there is the water release through the leaves. In between that, there is the water transport system in the trunk and the axis system. And the fourth important component is water storage. Water is stored in all living cells, but the entire water transport system functions as a water reservoir at the same time. The trunk is saturated with water in the outer area, in the sapwood, and this water reservoir buffers temporary fluctuations in water absorption and water release. We can prove the filling of these water reservoirs with so-called dendrometers, which measure the circumference of the trunk in very, very fine resolution. The trunk tightens during the day because its water reservoirs are emptied, and the underpressure in the trunk increases. At nighttime, the reservoir is slowly refilled, and it takes a few hours for the water reservoir to be entirely filled. The average annual temperature will certainly rise due to climate change. For the tree, that implies higher evaporation through the leaves. In order to ensure sufficient growth, these water losses have to be compensated for by absorption of more water through the roots in the soil. Most likely, the temperature itself will not be the dominant problem. 2 to 3 degrees plus on average compared to the temperature fluctuations that a tree needs to endure on a daily basis or during the seasons are not the big change. But if it becomes considerably drier with higher temperatures, this can certainly lead to problems, at least for some species. For example, we know that already spruce faces problems with increasing stress due to droughts in some areas in Austria. In addition, the vegetation period is further increasing and the dormancy phase during winter is shortened, which leads to even higher amounts of water withdrawal from the ground over the year. Overall, the probability for drought stress increases, even if precipitation remains the same. When precipitation remains the same, but temperatures change, the form of precipitation is different. Less snow, more rain. This means the change in the snow layer is very critical for vegetation, because a melting snow layer guarantees a continuous water supply in spring. If we have less snow in the mountains now, then this is a problem for plants or trees, even if, on average, precipitation remains unchanged. Precipitation patterns are the second important point. This means trees don't grow according to mean values. The patterns show whether it is a continuous water supply or whether the extreme incidents are increasing. And this is the second set of problems that we see and that needs to be questioned critically in regards to the growth of trees. How much water a tree needs primarily depends on the tree species, its size and location. A large broadleaf tree can absorb a few hundred liters of water daily and release it via the surface. If we look at the velocity of the water flow in the trunk, we find water in conifers to move at some centimeters per hour. In broadleaf trees, such as the ring porous oak, water moves meters per hour. A tree only has one way to regulate its water usage. It can reduce or close its stomata, which are tiny pores on the bottom side of the leaf, as soon as water stress increases or the transpiration suction becomes too strong. It does not like to do that, but that is the price in order to get carbon dioxide into the leaf for photosynthesis. Through evaporation via the leaves, a suction is created in the plant that pumps water up from the root through the trunk. This creates underpressure in the water transport system. All plants, and especially trees, are able to withstand a specific negative pressure. If evaporation and transpiration suction become too strong, the water column can break, resulting in long-lasting damages on the water transport system. This is particularly critical, as a damaged tree cannot sufficiently absorb water from the soil, even if the soil is sufficiently saturated with water. Thus, the drought stress for the tree is extended. And this is really critical for the plant. We assume that conifers, that lost more than 50% of their transport system, or broadleaf trees that lost more than 80% of their system, will die off. In a lab, the tearing of water columns can be shown by exposing plants to drought stress and by attaching sensors that track the occurring vibrations. These are acoustical stress tests with sound emission analysis. These beech trees are without water supply at present. The plants try to absorb water from the soil, and this creates tensions. These water columns become increasingly tense, and when tension becomes too strong, the column tears. And we can measure the stress release with acoustical sensors. In the beginning, only relatively few signals can be detected, because the plant closes the stomata due to drought stress. Later, tension increases, and with proliferating water stress for the tree, more and more water columns tear off during the daytime hours. The sound of breaking water columns can be transferred into frequencies that are perceivable by humans. In Norway spruce, it is mainly the early wood that serves for transport water. This is early wood from a spruce that is hydraulically sensitive. Cell walls are relatively thin, and the cells have large lumens for transport water. In comparison, a spruce with thicker cell walls and smaller lumens is less sensitive to drought stress. These characteristics are mainly genetic, but are also influenced by the climate. Research has shown that the characteristics of this early wood zone are impacted by the weather conditions in the preceding fall. If the tree receives a lot of rain during that time, the tree develops relatively vulnerable wood with thin cell walls and large lumens. If the following summer is dry, the tree struggles to keep up its water supply. Trees can only rebuild the torn water columns under certain conditions. Living cells are required to refill the transport system. A broadleaf tree that naturally sheds its leaves as a protection against drought stress has a lot of them. When enough humidity is back and the drought period was not too long, it may refill its transport system with water and sprout again, thanks to these cells. Whether drought-stressed conifers can regenerate their water supply is not clear at this time. Extreme situations play a special role here. One extreme drought period is enough to kill a tree. Consequently, averages in biology are of less significance than extremes. Our results, as well as those of many other international groups, have shown that trees are adapted to the drought intensities of their local site conditions, and thus also regarding their resistance against the breaking of water columns. The BFW used a spruce provenance experiment in the Weinviertel region for such investigations. This trial site is located outside of the spruce's natural distribution. For us, this location is particularly interesting because we were able to study how Norway spruce performs when things get really bad, when it gets really warm and really dry. We particularly addressed the question how the spruce deals with drought periods, because this entire region is notorious for having had long, regular drought periods already in the past. In the experiment, we saw notable differences between the provenance origins. Some spruces have good growth and stability, even at this extreme location. These genetic materials can be used as climate-resistant seed origins and for further breeding activities. But given the ongoing climate change, the major question is whether trees can adapt fast enough to keep up with the quick pace of changing climate. It is questionable whether trees can adapt, since the generation time of trees is very, very long. Norway's spruce is harvested after 80 to 100 years. So this is approximately the time span in which the following generation could be adapted. It could also lead to shifts of the occurrence of species or to an adaptation of the forest management, for example. Climate change will not only bring changes to our forest ecosystems, but also to connected economic sectors. For the first time, we have quantified the monetary consequences of climate change up until the middle of the century in Austria, through all concerned areas and economic sectors, and we see that the greatest three areas also include forestry. If, for example, our breadwinner, Norway spruce, is not capable of reaching its optimal growth in some regions, or if it is attacked more strongly by pests and diseases, that will have major effects on the domestic economy. Different developments are expected in each and every region. Higher mountain forests could benefit with better growth from longer vegetation periods through rising temperatures. On the other hand, a substantial productivity loss could occur mainly in the eastern and northeastern plains, as well as in the inner alpine basin, especially when the precipitation decreases. Since a tree life cycle lasts for decades to centuries, it is necessary to react now to the conditions of the future. Suitable tree species and genetic material well adapted and with high adaptive capacity are the prerequisite for healthy and productive forests in the future. For one, it is very clear that the selection of tree species is important. Due to this, it is of great importance that we offer guidance to forest managers at all levels, allowing them to plan for the future, taking into account the change in climate that awaits us in the upcoming years and decades. It is also very crucial that we take care of game management in order to prevent game overpopulation, which could place additional stress on our forests.